the AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia, and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, everyone. Welcome to the latest webinar of the year in our AI for Earth and Sustainability Science Discovery Series. I'm Maria Piles from University of Valencia, and we are creating these seminars together with Gustav Camps, Marcus Reinstein, and Joachim Denzler. We're part of the ELIS program of Machine Learning for Climate and Earth System Science. And today we are joined by David Schell from University of Applied Sciences in Upper Austria, Eggenberg. And he will be presenting a talk entitled Airborne Light Fields for Wildlife Observations. And I have here a short CV. I can briefly introduce you, David. He's currently a professor of visual computing at the University of Applied Sciences in Hagenberg. And he research interests include computer vision, computational photography, machine learning, and drones. He's particularly interested in optimal sampling strategies and novel algorithms for multi-view data, such as light fields. He graduated from the master's program Interactive Media, actually at the University of Applied Sciences, where you are now a professor. But then I see you moved to the Vienna University of Technology, and then you did the PhD degree at the Johannes Kepler University in Linz. And then you were a postdoc there also at the Institute of Computer Graphics at the Johannes Kepler University there. And then you're now a professor in Hagenberg and leading the research project BAMBI, which I think you will be talking about. And it focuses on wildlife monitoring in Austrian forests with drones. So I think more or less we have introduced you, David, but the floor is yours. We will be talking about 45 minutes and then we'll have time for questions. So please wait until the end of the talk to post the questions and then we'll have some time for discussion.
Thank you very much for the kind introduction and hello everybody. Just give me a second. We'll just start and share my screen. So hopefully that works. You should see my screen now. So thanks again for the introduction. Today I want to give you a tour on airborne light fields and why they are used for wildlife observation. And I will give you a general introduction into what light fields are and why we use them for wildlife monitoring. Yeah. So I will very briefly also talk about the University of Applied Sciences that I'm currently working with. Yeah. Then I will give you a very gentle introduction also into light fields, because for some listeners, this might be a new concept. So I will give you a very brief introduction to that. And then we will talk about how we can apply this light field idea to forests and why it makes sense there. Yeah? I will show you some use cases along the way, and I'm looking forward for discussions afterwards. Yeah. As promised, very briefly, where I'm coming from. So I'm at the University of Applied Sciences, Upper Austria, at the campus in Hagenberg. The university itself is a university in Upper Austria with 4 campuses that are very close to Linz. Yeah? And one campus is also in Linz. Just to give you some numbers, Linz is a smaller capital city of Upper Austria, and it has around 200,000 inhabitants. Yeah? And the size of the university is around 5,000 to 6,000 active students currently. Yeah? The campus in Hagenberg is like 30 kilometers away from Linz, and one of the campuses that the university has. And Hagenberg itself is a rather small village, yeah. So it has less than 3,000 inhabitants. So there is nothing else than the campus and the big software park where companies and so on live. Yeah. So
David, just to very quickly jump in, sorry, I can see
yeah.
that you're sharing your screen, but unfortunately, I can still see this sort of Zoom screen within at the top right at the top of the screen. Can you see that?
There is a button I could try. Does that help?
Yeah. Try. Yes. Perfect.
Should go away in a minute, hopefully.
Yeah. That's fine. Thank you. That's perfect.
Perfect. Thank you for the update. Yeah, so basically the campus is fairly new. So I've added a picture here from the 1990s. As you can see where the campus is right now, there was just a farmer's building back then, and this farmer building is still there. So this is like, this still remains and is part of the campus. And this image is from 1 or 2 years ago, and there are already new buildings. So it's rapidly growing in this very, very tiny village. Yeah. So it's quite something unique, I would say. Yeah. The students in Hagenberg are around 1,500 active students. Yeah. If you don't shy away from the remote area, I invite everybody that doesn't live too far away to also come and visit us at the university. Yeah. At the campus here in Hagenberg, we work with drones. Yeah. We use airborne light fields together with drones. And I want to talk about why we do that and why it's useful. Yeah. And what we work on is we basically work on light field-based detection algorithms together with drones. And as promised, I'll give you a very brief crash course into what light fields are to better understand the ideas that I'm later explaining. Yeah. And I'll just start very basic, and I would compare light fields now to regular images. So if you have a conventional image, you basically have a 2D representation that you can view in your monitor, and that's it. You take a picture, that's it. You have a 2D image, and you can view it. You can also do some sort of processing, but that's it. Yeah. And light fields record more information than just a regular image. They are 4-dimensional. So that means you can do various operations that are not possible with regular images. So for example, you can change perspective after you recorded a light field. And you can also do things like you can do synthetic refocusing. So you can simulate a large aperture and then do refocusing, something that you need to do with the conventional camera at once. And you basically take a picture then and then it's fixed. Yeah? So you cannot do refocusing. And especially this refocusing idea, that's something that we will utilize later also in my talk. Yeah. As you might imagine, systems that could record light fields would be, for example, camera arrays. So if you have multiple cameras stacked together, then basically the sequence of images that you get, or when you change the perspective, then you basically have a sequence of images. So one of the systems that could record a light field would be such a camera array. They are, of course, bulky, and you cannot take them with you. So there are also smaller systems that you can utilize for recording light fields. And those systems, they use micro lenses somewhere in the optical path in front of the image sensor. Yeah. And people might recall the Lightro cameras that were a few years ago on the market. They had this very iconic design. I've added a picture of one of them also on the slides. Yeah. And those are such micro lens based systems. They didn't have a breakthrough in the consumer market, so Lightro is gone from the market because they also have some disadvantages, but you can use this principle of micro lenses building inside the sensor, in front of the sensor, to record light fields in general. Yeah. And one of the applications where I can use this, where I worked a while ago on the topic, is, for example, to use it in microscopy. So you can build a light field microscope, and such a light field microscope has the advantage that you can do things like refocusing, changing the perspective after recording, also of microscope probes. That's something that that would otherwise require you to move the stage where the probe is lying on, or you need to move the probe itself. And with light field microscopy, something like that is possible. And it supports illuminating and also recording probes with this light field technology. So this is basically the two systems that are commonly used for recording light fields. The fundamentals behind light fields are, as the name suggests, because we have light in light fields, what we try to capture, or what light fields try to record, is they try to record light rays. So light rays that are, for example, in this room here, or the room that you are currently sitting in. And we as humans perceive the world by basically interacting with light rays that hit our eye, and then our brain and the nerves in our eye and so on react to the light. And then that's how we visualize and how we perceive the world. And in total, we have a bunch, or a large number of light rays that travel around in our room, and some of them hit our eye and help us to visualize the world. And all light rays that would be within a confined volume, or all light rays that would be in a room, can be described by basically 5 parameters that are the position where the light ray starts, and then directions where the light ray is going. And that would be a 5D function, then, if you would express this mathematically. You can restrict this within a volume. If you have this within a limited volume, then the problem gets easier. And if you even simplify it more, that you don't care about every light ray that is in the room, but you just care about light rays that travel off surfaces. And light that is traveling off surfaces is radiance. Then you just care about light that is traveling from surfaces, then just care about radiance, and then we have a radiance field. And radiance fields, for people that are involved in computer vision, might have heard about this term in the context of neural radiance fields and similar techniques. So there are techniques like neural radiance fields that try to describe the radiance within a confined volume. And neural radiance fields, as the name suggests, use neural networks to encode this radiance field in a very, very efficient way. The input for such a neural radiance field reconstruction, or for the algorithm, is a set of input images. So we have a set of images, and from that set of images, we can reconstruct this radiance. And this set of images that I'm just mentioning, they can also be considered as a light field. I will come to that a little later. But what we need is, we need this set of images. We also need to know the camera positions that were used for recording, and some parameters of the camera. And that's a light field. And in this neural radiance technology, a neural network is used to encode then the radiance field and to reconstruct the radiance field. And that works extremely well. That's a very recent paper that came out 3 years ago. And it allows you to represent a scene with such a radiance field, and then do novel view synthesis. And what I have on the slides is, of course, a synthetic scene, but that works also with real data. And I've just taken some videos from the original paper that proposed this technique in 2020. And what you see here is basically an animation of a view synthesis. So this is not a video where somebody is holding up the camera and moving it around, but it's really view synthesis from this neural network encoding. And this network representation is much more efficient than the original data in terms of data storage. So it's way less data than the original images. And this is a very vivid research topic with quite some variations also recently. And basically some very recent advances in this field are the Gaussian splatting techniques that maybe some of you have heard of. So basically this is taking this idea of neural radiance fields one step further, where you basically have a very efficient way of reconstructing the radiance field and also of rendering it. So this is a technique that allows you to do rendering in real time, yeah, at a very high quality. Yeah. Yeah, back from radiance fields, back to our planoptic function. So this 5D planoptic function would be very hard to capture. Yeah. Again, NERV only does a reconstruction and only cares about the radiance. Yeah. What light fields are, or one other way to think about light fields is that you just take a subset of this 5D function, and that is basically you take a 4D subset. Yeah? And you can think about this as you have 4 parameters that describe a ray. For example, you can use pairs of 2 coordinates on a surface, and that surface could be a plane. And what you lose in this way is you lose the length of the ray. Yeah? But for displays or for cameras, this makes perfectly sense. Yeah? And what we have now is basically the way how you can think about those 2 planes is when you think about the set of 2 images or the set of images that we were talking about before, then one of the planes would be the spatial domain. So that would correspond to pixel coordinates within an image, a specific image. And the other, the directional domain, could correspond to camera positions. Yeah? So we have basically a way of recording such a light field and also a way of imagining how such a light field would look like. So one ray in this setup would be 1 pixel of one particular image, and there might be another image with it that corresponds to a different ray. Yeah? And what we do is basically we apply this idea of using light fields, this 4D representation, together with drones in our research. So basically you can think about just flipping those 2 planes that I just showed you horizontally, flip that in the vertical setup. Yeah. And what we do additionally is basically we take a set of images that are coming from the drone, and we don't have any specialized light field hardware on the drone itself. But what we do is we have a single moving sensor, so our drone is moving around, and the movement is basically acting as a camera array. Yeah. And with this idea, we went out in the wild and did some experiments. And the first that I want to show you is an experiment that we did at a wildlife reserve at the Inn, close to the border between Austria and Germany, where we have a wildlife reserve where herons are nesting. And it's one of the larger colonies within Austria. And we were there at the end of the breeding season. And as you can see in the video, it's a pretty remote area on the water. It's hard to observe. And ornithologists want to observe it because of conservation reasons. So they want to see how many nests are there, how many birds are there, yeah, how many young birds are growing there in that region, to basically see some trends, if the population is increasing or declining, and possibly to counteract. Yeah. And we used this light field, this airborne light field idea in this context. What we did there is we went there with a drone. The drone has 2 cameras built in. So we had a thermal camera and also a color camera. The thermal camera in this context makes a lot of sense because birds have a very high body temperature. Yeah, and we flew roughly 10 meters above the tree crowns of that region and recorded 130 image pairs. Yeah. And flight in this setup was very, very slow. So we needed 7 minutes for recording this. And what we did afterwards is we did a 3D reconstruction just to visualize everything, and also to get the camera positions. For light fields, it's very important to have a precise estimate of where the camera was for every image that you want to use in the light field. Yeah? And by doing that, we have a light field data set, and we can apply all the processing techniques on the light fields that I showed you earlier. Yeah? And one of them, again, is we can do refocusing. And this is what this animation shows. So this shows this light field refocusing, where we focus from top to bottom. And what you see in this refocused images is always see animal nests and animals like popping out when they are in focus, and like vanishing again when they are out of focus. Yeah? And that works because the idea now is we have this synthetic focus, we have a synthetic camera, and the synthetic camera is much, much larger than the area that we are, or the objects that we are visualizing. So think about it as as an effect that you also have in macro photography, where you basically have a very large camera compared to the object that you're viewing. Yeah? And we can do this with the color images, so with the color light field, and we can also do this with a thermal light field. And here in this case, we are focusing from bottom to top. The number in the middle basically tells you how many meters from the bottom we are up. And as we traverse from bottom to top, you can see that some animals are visible, and they are visible both in the RGB image, and they're also quite nicely visible in the thermal image. So here you see, for example, 3 birds that were hidden there, or that were not hidden, but that were basically in this area. Yeah. And this light field rendering, or this idea of using this light field, helps the ornithologist basically analyze the area where the birds live. So what you can do is you can like use this refocusing idea and go through the volume and detect and find birds. Then you can like look at the birds in the color images and the corresponding color images, and you can also put them in the 3D reconstruction, because you always get also a very accurate 3D position of where the birds are. And we did that for this heron site at the inn in Austria. And in the process, we found 67 heat signatures, and most of them were nests. The nests are also warm because of combustion effects. Then we have young birds that were still in the nests, and we also had birds in the tree branches. You know? The species that we could identify with the help of the ornithologists were mostly black-ground night herons, and we also had some other birds from the heron families. Yeah? So we had some limits while doing that. We had to do a very slow flight. We also assumed static animals, birds that would fly away within the 7 minutes of recording. They would be a problem. So we basically need to improve there, but we have some improvements at hand. And what we applied, or what we did next, is we thought about, now we try to visualize animals that live in the trees, that also live on the tree crowns. We were also thinking about, can we also visualize something that doesn't live in the trees but below the trees? Yeah. And therefore we basically went a step further, and we were looking into forests. Yeah. Forests are one of the larger ecosystems that we have on our planet. Worldwide, it's around 30% of the landmass that is covered by forests. And our universities in Austria, and in Austria the coverage is even higher. So we have around 50% of forest coverage in Austria, with some districts even having a much larger coverage. And that's quite high also in comparison to neighboring countries like Germany or the Czech Republic. And what we did there is we applied light field sampling, or this light field technique, in forests to find things on the ground. And the first application that we had was we were looking for people for the application of search and rescue. So again, we took our drones, we flew over an area, this time a forest. We did a 3D reconstruction, a sparse 3D reconstruction, to get an estimate for the camera positions, and also to basically have a nice way for visualizing things. And then we applied this light field processing idea again, and we did this refocusing. And what you see on the slides is a refocusing from the forest top to the ground. And as you can see, this time nothing is really revealed on the ground. The problem in this setup is that when you have a denser forest, little light reaches the ground, and so you have a really low contrast in the color images. But luckily, we did the same also with thermal recordings, because we record both. We record color and thermal data. And when you look at the thermal recording, you see that in the forests, you have heat signatures on the trees, and you have strong occlusions, you have heat spots on trees, and it's very hard to spot anything in the images that I showed you earlier, or in the sequence that I showed you earlier. But when we apply this light field refocusing again and focus to the ground, you see that we can reveal 3 people that were hidden here in this area. Yeah. So they stand out quite strongly, and you can very nicely identify that these are that the heat spots that we found here, that those are 3 people. And we have a fairly good understanding of why this works and why it stands out as strongly. And I want to briefly illustrate this by showing you a synthetic example. So the idea is, or the model behind why all of this works is that you can imagine you want to look at an image, but this image is covered by something. In this simulation now, it's covered by green things that could simulate leaves. And we don't see anything that's in this image or what's behind this image. But what we apply when our drone is moving over the forest is basically the camera is moving, and we can still try to see the image, and the image would be the ground, for example. So what's happening is that the image is still static, but everything else that is not on the ground, so for example, the leaves or the green things that in the simulation on top, they are moving. And what light field rendering ultimately does is it's not taking one of those single images, but it's basically combining all of those images that I'm just showing you. So this entire sequence is combined when we do this refocusing. And that's something that I'm showing you right now. So this is basically the result of doing this refocusing and averaging all the images from the sequence that I just showed you before. And as you can see, with this technique or with this idea, you can reveal the target. And one of the requirements is that the occluders, so the leaves that were on top, they need to move in every image. And then this idea or this technique works. We can even go a little bit further and express everything in numbers. So this would be our target image. Then the image that we record when we have occluders on top could be modeled as some sort of binary image where you say we have foreground, background, we have the occluders and the image that we want to see. And we can express the number of occlusion that we have on the image as a percentage. And then the mean squared error is basically this percentage of occlusion that we have. So it's a very simple equation where we have basically something between 0 and 100%. And that is only depending on how many or how much of my original target is covered. And this looks a little bit different when we do this light field rendering. When we do this light field rendering, the equation changes. And we also need to consider the number of images that have been recorded. So the number of images that are within the light set or the light field set. And as you can see, also when we do this light field integration, we can unveil or we can reveal the target. And I've plotted this mean squared error curve with this equation that we have on this graph here. And you can see basically on the left side, we have the highest mean squared error when we just have a single image. And when we have multiple images that we integrate, we get a much lower mean squared error. And that is basically what light field rendering does. And that's why we can reveal the people on the forest ground. And something that you can also see is that improvements are already reached very early. So we don't need the 100 images that I've plotted here in this graph, but it would be already enough to have 20, 30 images or so. And this curve looks very similar also for different densities. So if the forest would be dense or not so dense, this curve would look similar. However, it's slightly scaled, so it's stretched. And when you do this plot with the density on the x-axis, then it looks something like this. And the takeaway here is that if we don't have any occlusion at all, so if it's in the open, it's not in the forest, then this light field rendering idea or this light field integral idea doesn't help too much. And on the other hand, if the density is too high, then there cannot be any improvements. So for example, if people are hiding under a roof in a house or so, then also there is nothing that can be gained of this technique. Our model that I'm showing here is a binary model, so it's just having foreground and background. We also have other models that would also consider more complicated distributions. But all of the models assume a uniform distribution of occlusion, which might not always be the case for some scenarios. However, in our experiments that we did so far in forests, it seemed to work out and quite nicely. It matched quite nicely. And this is the core principle of why you can see the 3 people lying on the ground here that nicely. Yeah. So what we also did is we trained a machine learning model to detect the people. And one of the key takeaways or one of the learnings from the experiments were that you can use unoccluded scenes for training and still get quite nice results, quite nice detection results in forests when you have the test data occluded. So what you can see here is a few examples from the training scenes that we used, where people were just lying open in a meadow without any trees or whatsoever on top of them. The green thing that you see in the color images is the safety net that we applied. And the test data that we used in our experiments were scenes where the forest was pretty dense and people were strongly hidden. And in the video that I'm going to show you now is we compare this light field object detection technique, where we basically use this light field refocusing and then apply object detection, versus not doing light field technology at all. That's shown on the left side. And as you can see, by applying this light field rendering idea, our detection results are much better than the single image. Yeah, and the results that I'm currently showing you, recording, processing, still relied on quite a few manual steps, and also it relied on a very computationally heavy 3D reconstruction for getting the poses, for getting the camera positions that we need for light field rendering. So what we did in follow-up work is we also looked at fast processing directly on the drone. So for example, we used GPS positioning directly coming from the drone sensors, and we relied on digital elevation models to focus on the ground automatically. And we also did some quite exotic experiments where we also had some camera arrays mounted on the drones. For thermal cameras, of course, something like that would be unrealistically expensive. And also for other use cases than search and rescue, it might also be too expensive to have specialized cameras or specialized equipments on the drones. And this is what I want to talk about next, which is the research project BAMBI, where we want to apply this airborne light field sampling idea for animal monitoring. So this is the research project BAMBI, where we monitor animals in forests, in Austrian forests, and we want to get this working with conventional drones without any special equipment. The core goal, of course, is to keep the biodiversity intact in Austrian forests. So healthy forests require a healthy animal population in both directions. So there shouldn't be an underpopulation of some animals, and also there shouldn't be an overpopulation of some animals. So some animals in Austria require regulation, and the research project would also hint at such issues. And the airborne light field sampling technology might be a tool for that. So what we have in our research project is data, as we currently show you. So we have data in a forest where we have recordings of a thermal camera and recordings of the camera. This data is coming from a conventional DJI drone flying at 40-60 meters height and at 3 to 5 meters per second speed. And the positional data is coming from the drone, and figuring out where the ground is for the refocusing idea that I showed you earlier, that is coming from airborne laser scanning data that is in Austria fully available for entire Austria. And this flight, or this video section that I just showed you, when we apply light field rendering, and again we focus from the tree grounds to the ground, to the forest ground. Sorry? Was just hearing some interference, sorry. Hopefully you can still hear me and see me. So this is basically an animation where we were focusing from the tree grounds to the forest ground. And what you would see here in the thermal images, that's also where I've highlighted things, is we have animals hidden in this area. So the rectangles show animals that were in this region. that were pretty hard to spot before. And with airborne light field sampling, we can unveil them and find them in the recordings. Yeah, one of the goals of the BAMBI research project is we want to make this airborne light field sampling idea possible and usable for wildlife monitoring in Austria, but in general. Yeah. And we develop tools, and we also create a data set for that. Yeah. So there are no available tools, and there are also no large data sets that have the requirements that you need for airborne light field sampling. And one of the big parts of the project is also that we record the data. Additionally, we work on tools for doing annotations on the animal or on the recorded data. And those things we will later integrate in an AI model that helps us, or that should automatically be able then to detect animals. And compared to our search and rescue experiments that I showed you earlier, we can process much more light field data right now. So we process flights of 20 minutes and more. And that's something that wasn't possible with the experiments that I showed you earlier. So for data recording, we currently use infrared and color videos. And we also require additional sensors coming from the drone, like we use global positioning satellite data. The cameras, they need to be calibrated. And I already mentioned the flight speeds and altitudes that we typically take. And our data set, we started recording in April 2020, and we have around 40 hours of flight footage at the moment. And we record animals in the wild, but also in animal enclosures. And we try to get a variety of sites where we can record animals. We use typical DJI drones, for example, the Mavic 3D drones or the M30T drones from DJI for the recordings. And the animals that we have in our recordings are also quite a variety, but we have some major or some main animals that we focus on because they're important in Austria. And those animals would be red deer, roe deer, chamois, and wild boar. So those are the 4 animal types where we try to get a pretty large data set. The other animals basically are also in the data when we also record them, if we have a site where also the 4 other animals would be located. Yeah, for labeling and for annotating the data, we have our own tools because, as mentioned earlier, this light field data can be quite challenging to process. So what you see on the screen or on the slide is basically a screenshot from one of our tools. And the annotation of the data set is done by experts. So we have wildlife biologists in the project that take care of labeling the animals. And what we do is we annotate them with bounding boxes, and we annotate the species. And if possible, it's sometimes hard in forests, for example, we also try to identify age and gender of the animals for our training data. Yeah, while this screenshot might look like a regular annotation tool that you would also find out in the wild, what we additionally have, because of the ALFS or the airborne light field sampling technique that we're using, we have some additional properties and some additional processing capabilities, of course. And one of them, for example, is that all our labels, all our annotations are geo-referenced and are 3-dimensional on the elevation model. So, for example, I'm showing you a short sequence that demonstrates this. So what we have is basically we have the bounding boxes on a 3D mesh, and you can see that basically the 3D mesh has some height and terrain variation, and the animals, the annotated animals, are also live within this 3D context. So we have basically this additional data or some additional properties for every animal that we have in our data set. And this additional data or this additional information can also be used in other contexts. And one of the last examples that I want to show you, what we did within our research, is we utilized this geo-references that we have of animals when we apply our light field processing for further applications. And one of the further applications that I want to show you is for road safety. Yeah? So for example, we basically want to figure out if animals are close to streets. Yeah? So why is this important? Because in Austria, we have 130,000 kilometers of streets, and already talked about before that we have a quite high coverage with forest in Austria, and those two things would overlap in quite some areas. Yeah? And in those areas, we have quite a high risk of traffic accidents with wild animals. Yeah? So what we want to figure out is, can we classify or figure out regions or find regions where the chances of having a road accident with wildlife would be high. Yeah? So here you see a road section that is not so far away from where I'm currently at, so that's very close to our university. And what we tried there is we tried to assess how many animals might be very close to a road. Yeah? And we used this with the technology that we also developed in BAMBI, and we did this together with a collaborator with the KfW from Austria, which is a Austrian insurance company. So what you see here is now a top view or a satellite view of this road that you've just seen in the video. And what we want to investigate is how close move the animals to the road. So we defined a region, a test region, where we said we would do drone flights and we would try to count the animals. And what we did in this project is we have been flying at 4 different times of the day. Yeah? And every flight that we did in this area was around 20 kilometers long. So we had a total 90 kilometers of flight distance that we did in this area. Yeah? And on the next slides, I'm going to show you some results. So for example, when we fly in the morning, we found some roe deer and some rabbits, but not so many. And the numbers increases as we progress through the day. So in the noon, we had a higher number for both animals, and it was highest in the afternoon and declining again in the evening. Yeah. So what you see is, although it's the same area, it's a pretty limited or restricted area that we have used for our tests. You see that there's quite some movement going on. So animals go in this area, move out of this area again. And what we tried to model from this is we wanted to model how strong is the movement or how strong is the closeness of the animals to the road in this section. And this is the visualization that we came up with. Yeah? So based on these animal sightings that we have, we predicted some sort of closeness to the road. Yeah? And as you can see, areas where animals are very close or animals have been spotted very close to the road, there also our heat map is the highest, and that's also like shown in the road section that's also highlighted. The model that we use for predicting this is we just use some Gaussians to model this probability. And again, this was also the road section that you have seen before on the video. Yeah. And getting such data or such information might be very useful for decision makers to make streets more safe. So for example, to place warning signs at certain road sections, or to apply speed limits, or use acoustic warners to shy away animals in certain scenarios. So this is one of the applications where we applied this technology from BAMBI also for a particular use case. The research BAMBI project, or the BAMBI research project itself, is still ongoing. It runs till 2025. And we're still in the process of collecting more flight data and developing our tools for working with the airborne light field sampling data. And we also train AI models and evaluate them as we progress. And although it's in industrial projects, the findings that we have in BAMBI, including tools and data, will be open sourced. Yeah? So the data is not finished yet. It still needs to be annotated, but we have some intermediate data already. So if somebody wants to use that for their own research, let's get in touch and we can share the data, or we will find some way of how we can help each other. Some of the software that we are developing in BAMBI might also translate to other problems. For example, in Austria, we have a quite strong project related to fawn rescue, where hunters try to save fawns from fields before the grass in the fields or before the grass in meadows is cut. Now that's a big problem in Austria because small fawns have this natural instinct of hiding in high grass and not moving at all, even if somebody gets very close. And what I've brought with me is as a short video that shows you of how still they typically lie. So what you see here in this is we have basically a zoomed-in version of showing you the fawn, and then we have a rescuer that's approaching the fawn. And as you can see, the rescuer was very, very close to the animal already, but didn't see it because it was hiding so well, and the animal also didn't move. Yeah. In this case, the fawn was already more mature, so it was strong enough to run away by itself. But younger fawns, they wouldn't move at all. They would just duck and cover, and that, of course, would be their death. There's an initiative in Austria going on for saving the fawns. And the technology that we apply in BAMBI would also work here. Of course, it's not within forests, but outside. This technology that we utilize would be also very, very useful in this context. Yeah. And the last phenomena that I want to mention that we encountered in the BAMBI project is when we recorded animals and when we recorded footage in winter, then what you could also see is that the tracks of animals in the snow are very strongly visible in the thermal recordings. So what I'm showing you here is a short video sequence where you see the color image and then the thermal recording side by side. And as you can see, this is within an animal enclosure. That's why there are so many tracks, but the tracks pop out quite strongly in the thermal recordings. And we need to investigate this a little bit further, but this might also be a potential use case or a potential application where you could basically use drones and thermal data to basically get an estimate of how many animals or get an estimate for an animal population based on the tracks of the animals. So you don't need to find the animals itself. And that would be very, very useful for shy animals that would flee if they hear a drone or if they see people. But further tests are required in this context, but it might be a promising future direction. Finally, I want to say thank you to all my collaborators in the past years, also from JKU. But on the slides here, I have colleagues that work and or have been helping with the BAMBI research project. So there are colleagues that currently are working here at the University of Applied Sciences. And also the project's partners that are involved in the BAMBI research project. And finally, I want to point out also something else. So for people from Germany that speak German, what I have on the slides as well is the BAMBI research project is also featured in German TV tonight on the ZDF in one of the Terra X episodes called The Alps, Meine Alpen. And there you can also see BAMBI featured in this TV show. And it's also already available on the broadcaster's website online. So if you feel like watching some more BAMBI tonight, then I invite you to basically turn on the TV if you live in Germany or Austria, of course, or maybe also Switzerland, that I don't know. That would be one limitation. Yeah, and with that, I want to end my talk. Thank you very much. And I'm looking forward to questions and to answer them.
Thank you. Thank you, David. Can you hear me?
Yeah, I can hear you.
Okay.
Yes.
Okay. So you're going to be on TV tonight. This is a big day.
Yeah.
You are on the
actually my colleagues that are on TV. Sorry, but
okay. So, but the project,
the project
which
would
your BAMBI project. Good. Good to hear. Thank you for the very nice presentation. I really enjoyed learning about this light field imaging technology and seeing in very high detail, from the drone. And yeah, it's very interesting projects. I have some questions. So I think at the moment we don't have any message on the chat. So I can just post some of them. So first of all, I wanted to ask you if you think there will be some value into adding more bands in the thermal spectrum, because you're just using RGB and one thermal band. Perhaps for the classification, which I think and maybe some. I'll ask later about how challenging the classification is, but perhaps having more bands would help.
Yeah, that's a very good question and a good idea. I could imagine that helps. So what we try to achieve is basically we want to utilize the thermal band and alongside with the color band that we have. And you would have like other infrared bands, for example, like near infrared bands that would be nowadays already used for detecting plant vitality. So that could be also an indicator or something that we could track alongside with looking for animals. The other bands for finding animals, that's something that I would need to investigate, but it is a very interesting question. It could be that basically some animals stand out more in some other ranges, yeah. Because in the visible range, the range that we as humans see, they are pretty hard to observe. Yeah? So I have also some videos of Capra ibex that they are super well hidden in the color images. You only can spot them because of the thermal data, because of the heat signatures. So the natural camouflage from the animals, especially from the air, is pretty good. It might be that other bands would help. Yeah, that's a good idea.
Okay, of course that makes the system more expensive, so this trade-off. But it would be cool to test, right?
Yeah. Yes. Definitely.
Okay, and then about the validation, because you saw this very nice annotation tool, but then you really need expertise, right? To actually, so do you have a team of biologists or people?
In the research project, we have like technicians like myself here that have an IT or informatics background like myself, and we work on the processing techniques for the research project. And then we also have wildlife biologists that basically do then have this expertise of classifying the animals correctly and to help us. And it's also their work of doing the annotation and labeling the animals. That's something that I couldn't do, to be honest. Yeah. So we try to get a really high quality data set, and therefore we have those people on board for the project.
And for training, I'm just curious, for training the classification, do you use like photographies of those animals as well, or you just use
No, we just used we try to just use the light field data. So,
okay.
And a lot of the training data that we are currently recording is in animal enclosures, where it's also easier or a little bit easier to label the animals correctly, because you would know in this enclosure there would only be 2 species maybe, or there would be only 1 species, and then you could label them also more accurately. No?
Oh, makes sense. Okay, it makes a lot of sense. Nice. And then I was thinking of to measure now when you plan these campaigns, you need to have a sampling strategy, right? There's this optimal number of images, which is around 20, you mentioned, no, in the graph.
Yeah.
But how you measure how many drones do you need, or depending on the area?
So that's an open question also in the research project that we have also spent some time on discussing within the team. So the current strategy would be, so for the training data, what we do, so we handle training data and then the evaluation phase differently. So we have training data where we try to get as much data or as much images as possible from the animals. So we fly there very closely with the drone. So the drone is like flying in very small gaps over that area where the animals would be. And for the evaluation, when we go out in the wild and want to cover a larger area, one of the limitations would be that the areas would be too large to basically cover with one single drone and with one battery. and also the distance would be quite large. So with current drone technology, you have some limitations there. And our idea so far is that we will try to basically do some sort of random sampling where we say we fly transects over the areas that are interesting for us, and then we would do some sort of extrapolation and some density estimation that is sampling based. There are similar models that can be used, for example, if you have camera trap data, where you also just have a very limited view of the entire forest, where you also do some sort of extrapolation of how many animals are really in this region. And they also consider some biases. And we believe we will take one of those approaches also for the final evaluations.
Okay, also for the sake of time, right? Because you need to cover a whole area, and you have, okay.
Yeah.
So you're also taking that into account. Makes sense.
Yeah.
And then for being more into the machine learning approach, how do you do this object detection? What approach do you follow to get the?
So for the search and rescue, and also the first detectors that we have trained, they would be image-based detectors, but really, so we would basically use object detectors in the images, and we will, just like with the search and rescue experiments that I showed you, we will basically train them on the single images, and later on we will also train them on the light field renderings, and we will basically then have a good baseline to compare things. And we also have some ideas for improvements for not using standard object detectors, but using more advanced techniques where we basically don't use this light field integral idea that I explained with this equation also earlier. We have some ideas there, but we need the data first to basically evaluate this if things like that work out.
Okay. And when you do a new experiment in a different forest, do you need to train everything from scratch, or you can also leverage from your older models?
So the idea would be that we have a set of images that have been recorded in enclosures and in controlled situations where we know what the animals are, use that for training, and then we can go in the wild and basically detect animals there. Of course, we would also have we will also require some sort of control set where we can also have a controlled setting, controlled environment where we can then verify how good the algorithm really works.
But you can benefit from your past experiments being in Austria, right? For the BAMBI project, because I guess there will be different kind of forests and animals, but all in all, you can just cover territory.
You mean if we extend it to different animals as well? Yeah. Yes. Yeah. Yeah. There we will probably need more training data. Yeah. Probably. Yeah.
Okay.
Definitely. Yeah. Let's put it like this.
So in BAMBI, you're targeting the main animals.
That was also that was also coming, or those are the animals that were suggested by our biology experts. They were saying in Austrian forests we have those 4 animal species that can cause problems, and they would be important to monitor, and that's why we currently focus on that. But ideally, it could be extended to any other species. But for some, it would be definitely a problem to get training data. If I think about wolves or things like that, it would be hard to. I mean, wolves maybe in enclosures, but you would not find them in the wild that easily.
Yeah, I agree. And then I particularly like the way that you use the technology to try to understand where the animals are during the day. So you do these flights, and then you see more or less at what time of the day it may be more dangerous to pass through the road. And you did that at the daily scale, but did you actually look at seasonally if the animals actually have different?
For the project we just did it, that's a very good question, but for the project we just did it like once in a sequence of 1 or 2 days. But that would be very interesting. That's also what the biologists told us, that we should extend this and do this like seasonally and in a more regular interval. And that's maybe also one of the applications for BAMBI. If things work out, if the detection works reliably, then you could also use the technology to basically get monitoring or distributions over the seasons and over the years. Yeah, so you can like monitor how does the population change within the season, but also over the years. Yeah, so the time scales. There might be multiple time scales that are interesting. Yeah,
It will be super informative.
yeah.
It is really nice line of research. Let me just check the chat just in case. Okay, that's good. I have one more question. And then I think it's okay. We can go to the jazz part. And it's about satellite data. I work with satellite data, and then if we could do the match somehow of what you learn with the drones, with the satellite image, that would be super interesting, because the satellite data you have regularly.
Yeah.
But the spatial scales are really different, right? Because you're in centimeter scale. So what's the detail that you're getting with the drone?
So the thermal camera is also quite limited. So we cover, let me do the math. So we cover roughly 50 by 50 meter on the ground when we fly at 50 meters height, yeah, with our thermal cameras. And they also just have a pixel resolution of 512 by 512 pixels, something like that. So it's also not so much on the ground, but it's definitely more than satellite data, at least the satellite data that I know of that is available.
Yeah, as the satellite technology is improving and the Copernicus system is providing like more regular visions of the Earth and RGB and thermal particularly, perhaps it will be, if at some point we can try to learn with machine learning, you know, the relation, the drone imagery and the satellite paths, if there's some connection there, that would be very powerful.
Yeah, I mean, I had a discussion a while ago. It would be, for example, interesting to use satellite data to figure out where it wouldn't make sense, yeah, to basically detect or do some pre-classification with the satellite data, where you would see certain habitats of animals and where you would like to have a closer monitoring technique. Yeah, then it could be that you have a first step of using satellite data or for an area, for a pretty large area, that gives you then estimates where animals might be, yeah, or where the number of animals needs to be assessed. And then you would use a smaller scale technology like what we use in BAMBI to really do a more precise counting in those regions. So I guess there is definitely some synergies there.
That's very interesting. So the BAMBI project is it when did you start it?
It started 1.5 years ago.
Okay.
And it's a 3 years project, so it will stop in spring 2025.
Okay, and hopefully you can continue
Hopefully
the
we'll
line
have
that.
more interesting topics then, yes. Yeah.
Okay, so yeah, we're out of time. So thank you very much for your contribution to the webinar series. It was a pleasure to have you here. Thank you for the nice discussion.
Thank you. It was a pleasure to be here. It was a nice opportunity to present what we're doing.
And to all the people that is listening, we will go now to this other room where we can just discuss in the chat in case you have questions. Okay, thank you very much.
Thank you.
Bye.
Bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.